Hi, friends. Welcome to an exciting episode of Quantum Computing Police, in which I talk about quantum computing and typology. Okay, so the reason is this: I want to read this little article, this little piece of this article I'm reading here. It's interesting. First of all, you should look at this chart here. So these complexity classes refers to uh, okay, so P is problems that can be solved by a classic computer, no problem. Like, how many eggs are there on your face? Easy one for a good example. Like, how if a person travels, basic math problems. Like, if a person travels 60 miles an hour and at a constant rate for 500 miles, how far does he travel? Or something like that, basic math problems. That also includes, that's an example of NP2. The answer can be checked quickly. So it's easy to see if the computer's right or not. BQB is all problems that quantum computers can efficiently solve, which includes all problems that our classical computers can solve. That's already been proved mathematically somehow. I don't know. But then I'll read this next part. What can a quantum computer do that any possible classical computer cannot? Computer scientists have finally found a way to separate fundamental computational complexity classes. In 1993, computer scientists defined a new complexity class that they called BQP for bounded error quantum polynomial time. They defined this class to contain all the decision problems with a yes or no answer that quantum computers can solve efficiently. Around the same time, they also proved that quantum computers can solve all the problems that classical computers can solve. That is, in BQP, BQP contains all the problems that are in P. But they could not determine whether BQP contains problems not found in another important class of problems known as PH, which stands for polynomial hierarchy. Polynomial hierarchy is a generalization of NP, which means it contains all the problems you get if you start with a problem in NP and make it more complex by layering qualifying statements like there exists and for all. Look at this example over here. Over here. When thinking about complexity classes, examples help. The traveling salesman problem asks whether there is a path through some number of cities that's shorter than some given distance. It's an NP because it can easily be checked. The answer can see if it's shorter because it just has to compare one number against another number. A more complex problem asks if it's the shortest path through these cities is exactly a given distance. That problem is in pH. It's not easily checked. Okay, so that's what that says. Anyway, classical computers today can't solve most of the problems in pH, but you can think of pH as the class of all problems classical computers could solve if P turned out to equal NP. In other words, to compare BQP and pH is to determine whether quantum computers have an advantage over classical computers that would survive even if classical computers could uneffectively solve many more problems than they can today. Okay, so that's whatever. To the extent to which you understand all that stuff is not really super relevant here, except I like this complexity class idea. The best way to distinguish between two complexity classes is to find a problem that is provable in one and not the other. I'm assuming this should be an E. Yet, due to a combination of fundamental and technical obstacles, finding such a problem has been a challenge when it comes to quantum computing. If you want a problem that is in BQP but not in pH, you have to identify something that by definition a classical computer could not even efficiently verify the answer, let alone find it, said Aronson. That rules out a lot of the problems we think about in computer science. But it doesn't rule out personality type. That seems like a perfect thing for this to be applied to somehow. I don't really have any good ideas of how or anything, but I bet some people with TI in number one stack or TE in the number one stack, number one slot, they could probably think of some things. So I wanted to throw it out there that we should try to get quantum computing people interested in typology and see if we can improve on the existing assessment protocols. It's like right now I feel like I could beat a computer, no problem, in typing somebody. I don't think computers can hang at all in that contest. Like, they can beat us at chess, they can beat us at Go, they can beat us whatever. I don't think a computer can beat me at typing somebody. So, isn't that a great problem for this to address? I think so. Anyway, I just wanted to say all that stuff, and thanks for watching. Don't forget to eat plenty of cheese.